Okay, fantastic. Great. Okay, so this week we're releasing Bittensor 2.0.4. So this is a couple changes to the code base, a bunch of things that will be minorly noticed by you guys, which are optimizations on our side, but I'm going to go through a lot of the major updates today. So, but before we do that, let's talk about the network and how it's growing. One of the most interesting things is the number of active miners. I mean, usually we talk about this because it tells us how much compute we have on the network. And if everyone were running $5 VPS machines, we've got $5,000 worth of compute per month. But I think it's probably substantially more than that, because we've hit up to 1,054 active miners, and people are now running some substantially, like at least on the Open Tensor Foundation side, we're running some pretty good compute, and we're seeing an exponential growth really in the last couple blocks on the number of active miners. So the system is filling up with the number of peers. So we're already at 52% capacity on the 2,000 UIDs. When this reaches 2,000, we'll probably expand the network. But as it reaches 2,000, we expect the competition to get your miners into the system to really push up. For instance, the work required to get into the network should jump significantly, and the computational burden that's required for miners will also jump. As for token inflation, 5% roughly of the tokens have been emitted of the 21 million. So we're moving pretty fast. It's 1.2 million tokens outstanding, and a good 82% of that is actually staked in the system. So people are staking tokens almost entirely. We're at 82%, which is I think pretty fantastic. There's clear demand right now for people to stake tokens and keep them on the system, and that's what we want, because the more that people are validating, the more distributed that the token is on the system, the more protection we have against a 51% attack of any sort. So that's great. So we have 82% total stake staked. This is probably on a good portion of that is on servers, so it's not validating. We were looking at about 18% of that is on servers, and then the remainder of that is actually on validators. So these are some pretty good numbers. We're happy about that. Our work looks pretty healthy going forward. Another thing we're interested in is the neural capacity. So how big is the Bittensor network right now? We don't expect to be pushing to the limit right now because it's just super early days, but with about 1,054 active miners, let's say people are running GPT-2, about 170 million parameters per model, we can say that we have an active parameter set, or an estimated active parameter set, about 123 billion, which is quite significant. So I put together a bit of a chart here. This is over the last few years, the largest models were GPT-2, GPT-J, Megatron, T5, Bittensor, and GPT-3. GPT-3 was obviously, head and shoulders above the largest language models of the time, T5, and we're right there in the middle. So in about 3 months, we've gone to about 123 billion parameters, and if we can get up to 180, 190, we can surpass GPT-3. This is not the largest. GPT-3 is no longer the largest model in the world, but we're putting it there as our kind of pie in the sky. We want to try to beat OpenAI's best-in-class model. And this is estimation, because we don't really know how big the network is. We're just using this 117 million parameters per model that's active in the system. People could be running larger or smaller models. Perhaps people are running really small Albert models. Until we get some feedback from the community, we're just going to use GPT-2 because it's the biggest model. We want a server without specifying anything else. It's about 117 million parameters. Cool. Token distribution. These are newly updated today. This is what the hotkey on the left. We can see hotkey distribution. So these are likely validators. The large stake supplies validators, and the bottom end of that graph are likely servers. So a fair amount of distribution or decentralization across hotkey accounts, but the more important thing is across cold key accounts, because that tells us the likely distribution across individuals. So we still have some centralization in the cold key account balances, but this is subject to change, I think, pretty quickly, especially as distribution continues. Where are we? This is an updated graph of location. On the left, we can see that so about 50% of miners are on other VPSs or running at home. Their IP addresses don't say either Contabo or DigitalOcean, and about 50% of miners are running on DigitalOcean and Contabo. So that's interesting. A lot of people are using those two VPS providers. The foundation is using those providers, and Contabo seems to be a pretty cheap option that people are using. It's quite interesting. That's why we see this clustering around Germany on this graph, as well as in the eastern and western coasts of the United States. That's usually DigitalOcean, and this is fine, but we would prefer to have more geographic location decentralization in the future, hopefully in South America and across Asia, not just in Europe and in North America. Great. Okay, so this is the network update. I'm going to stop here and maybe ask people if they have any questions about that update before we go into the code updates and other optimizations we're doing to the API.
Folks, feel free to even ask questions in the general channel field, so you don't have to actually speak up if you don't want to. Okay, I think we're good.
Okay, we're great. Cool. Well, that's just a rundown. We're probably going to do this every TJF, just to get an understanding of the network, how things are moving. Parameter counts, I think, a really important one for us, as well as the activity. Eventually, these will just be displayed on a dashboard, and you guys don't need to come to this meeting. But for now, we have to build these graphs ourselves. Cool. So over the last two weeks, we've been working on network optimizations. So Bittensor optimizations. There's two major ones that I want to talk about. So we have two compression techniques that are implemented into the current stack, but not necessarily enabled by miners. So the first one was a gRPC compression technique that Eugene implemented. So that was a 10% drop in bytes per request. And the second one was a float 16 compression, pushing, which is 100% compression actually from float 32 compression on the wire. This is where we want to get a lot of the speed gains going forward. It will be compressing things on the wire. So, for instance, our gradients are full float 32 compression, but there's research out there that shows that we can get away with even single byte compression on our gradients. And we could probably pull down the compression on the representation sides down to float 8 or even float 4. Maybe not float 4, probably float 8 is possible, which compress another 50% on the wire. So these are sort of back-end optimizations that you won't really notice if you're running your miner, unless you look at the query times and the number of queries per second that people are running. So this was a great update from Eugene over the last couple of weeks. Yeah, I think one of our biggest pushes right now on the code side is opening up the Bittensor API to use multiprocessing. The miners right now are single thread miners. They work pretty well, so they take advantage of that thread as much as they can. But in terms of querying the network, for instance, making requests through the Dendrite, multiprocessing is super important. So we've been studying and building out the tools to run multiprocessing requests over the network, and this is where we think that we'll get a lot of the speed uptake or the speed improvements over the next couple months. Just a preliminary results show a 4x speed increase by running multiple processes doing queries. So clients that are talking to the network, if they're using this updated API, they get actually a 4x improvement in speed. So that's another update that we're really happy about. It's optimizing the API to allow people to really talk to the network with high fidelity. I think the thing that most of the miners in the chat will be interested in is release of a new miner. So we had the advanced server template miner, we had the signal validator, and now we have Multitron, which is the first miner to take advantage of multiprocessing. It's a lot more difficult to run, so we're going to have to help you guys get that up to speed. But what we can get out of using multiple processes, if you have multiple devices on your machine, if you have a CPU and a GPU, you can take advantage of the CPU and the GPU when you're training. And the Multitron server also takes advantage of multiple process training, which shows that we can actually speed up the distillation, the training of the nucleus, and it can service requests a lot faster. So I think this is what's going to be interesting to people is using this server to take full advantage of their entire compute infrastructure. So if they have multiple CPUs, they can take advantage of it to service requests. Isabella, you have a tutorial on Notion, I believe, for people to run this. Is that correct?
Yeah. So it specifies like what kind of configuration that you can give for the Multitron. Like for example, you can set like the number of processes you want, and then if you want to run it on GPU or CPU, that kind of thing. So.
Yeah, that's great. So that's a Notion tutorial that people, Isabel, maybe we can actually build a Discord channel directly for this new miner, and people can ask questions in there to really stress test it for us. I think it's still an experimental phase, but we think that eventually people will only be using this miner, and we'll probably deprecate the advanced server because everything and advanced miner. So that's really exciting. We got a cool name for it, Multitron. It's basically just random, except for the multi-part processes. And this is all pushing out today. So at the end of today, you should be able to access this new miner if you want to try things out. Cool. Behind the scenes, we're doing a lot of research to investigate various caveats to the system, making sure that the ranking method is improved, and also that the system is resistant to adversaries. So last week we talked about how the Flaubert models were doing incredibly well, and we actually discovered why that was the case. The original Bittensor paper talked about a method called Fisher's information metric, which is a mathematical tool for calculating the informational significance of a signal. So the validators, what they do is while they're training, they evaluate the informational significance of every miner out there. However, the assumption in the paper is that the validators have reached what's called a local minimum. It means that they've come to a rest in their training procedure, and at this point, the score is always has a high magnitude for peers which are informationally significant against the loss in a positive way. So it means that they're actually improving your loss. But until you reach this steady state in the training, the sign of that calculation can be a red herring for the information of the peer. So you can actually see that it is informationally significant that this peer is not what you want. It's the model is actually saying we want to remove this peer instead of saying we want to keep it. And so last time we talked, we were talking about the ranking accuracy and how it was pushing French models that were doing quite badly up into the ranking statistics. You can see here on the right side how Flaubert model was actually performing best out of all of them. And this was caused by this training procedure not at a local minimum error. And so what we've done is improved the validators to keep track of the magnitude of the Fisher's information and the sign of it. And so a ranking accuracy is quite improved. So you can see on the right here that the new rankings measure the sign of the informational significance, and by removing this local minimum assumption, and we actually get a much more accurate measurement of the models in the network. GPT-2 in this case coming at the top. So that was exactly what we wanted. This is all kind of going behind the scenes, so you won't necessarily notice that, but once we push this to validators, we hope that we'll get a much more accurate ranking and against which people can tune their models or into the incentive mechanism. Let me know if you guys have any questions. Just interrupt, TACO has been working on something called adversarial resistance. So we're not going to talk about the adversarial attack itself, but what we have been investigating is ways of determining models which are attacking the network by sending the wrong embeddings. And on the left side, you can see our adversarial detection method actually picking up this behavior on the red line, where as against the brown and blue lines here. So this adversary is attacking the system, and the validator should be able to detect this given our new adversary distillation method. We also have been proving that the network is reaching synergy and ensuring that the validators are able to measure the synergistic value of the peers. So this is really important for Bittensor, is making sure that not only is your miner valuable in the network, but it is uniquely valuable. Is it synergistically valuable? Does it add something that makes other models better? And so we've been evaluating, we've been ensuring that this is the case for our validators, and it turns out that is the case. So that's really awesome. Yeah, outreach. Okay, some other updates here. We released our Explorer. You guys are welcome to go check this out. Probably tomorrow. We're gonna launch this on Friday.
Just to add a bit to what Jake you're saying just now, that URL might change. It might just become explorer.bittensor.com. Just as a heads up. If it does, we'll let you guys know.
Yeah, great. So yeah, anyways, the Explorer is out probably Friday. Is that right, Ala?
We're aiming for Friday. Yep.
Okay. Great. So this is great. So on the Explorer, you can create accounts, you can transfer funds, you can see total issuance of the token, and you can actually investigate blocks as well. So that's pretty cool. And it's the first push for us into having a full-on Explorer that people can use to change, between different networks and move funds. And finally, we have two blogs. I want you guys should go check this out. They're on our Medium. Go give them a clap. And yeah, if you can connect to them from our website. So if you go to bittensor.com and then go to blog, you can read about some of the philosophical underpinnings of what we're doing. And that's it. Yeah. So let me know if you have any questions. Anybody in anything really?
Cool. Looks like everyone got it right away.
There's a lot there.
There's lots of process.
And yeah, there's a lot to process there. I mean, we talked about compression, we talked about adversarial resistance, we talked about the Explorer, the network stats, and yeah, there's the slides I'll release after this call, so people can go through them themselves if they want. And yeah, if you have any questions, let us know. Post them in the general channel.
And if not a problem, because we also are recording this finally properly. So we'll be posting it on YouTube soon. Yeah.
Cool. Great. Cool. Well.
And sorry. Yeah, my one thing that I was going to mention is, well, again, guys, if you have any questions or anything, please feel free to kind of post in general or anywhere.
Can I ask a question?
Please go ahead.
So you guys are all AI experts or building with NLP?
Yeah, thanks, Codex. Yeah, so GPUs are a big push for us right now because almost every miner is probably running on a CPU.
Yeah, so you want the GPU.
The GPUs will be super important.
Jake,
I think he's asking something else.
someone else is talking right now.
I can't hear them.
But You can hear me, no?
I can't hear you. Also.
Oh, what is? Sorry, Baron. I think Jake and Isabella might be having some issues. Do you mind saying your question again?
Oh, he's
I was
muted
just-
for me. I don't know why.
No, really? Like, you guys can hear me.
Yeah, I
Who
can hear you.
hear me.
I can hear you pretty well. I
Yeah,
think it's
yeah,
only
I
Jake.
can
Can you hear me? Yeah. Yeah. So I was
Yeah, go
wondering,
ahead.
like,
Go ahead, Barry.
what you guys, what the expertise of you guys is in the field. So I'm going to say something about myself. I'm not
Alright.
the most
we can hear you.
tech
You
savvy.
can go ahead.
Yeah, you hear me?
There's some weird crosstalk
Okay.
going on.
I can hear you now.
Yeah. So, anyways, I'm not the most tech-savvy person in the whole field, but it's for me it's quite interesting in to know who is doing what they're doing in respect to what your studies were, what your expertise is. I think that is quite interesting to know.
Yeah, I can answer that question for you actually. So myself and Jake,
You
can you hear me?
you are Ali Shah. You're Ship, but
I'm
your
Ship
name
Ship.
is
It's Allah, just ALA.
Allah
That's my- yeah.
Allah Shabana.
That's right.
Allah
That's right. That's me.
Shabana.
Yep.
Yeah, I saw you have some good Google Scholar sites.
Yeah, that was a long time ago.
2012.
Yeah. Very old.
Yeah, so that's cool. That's
Yeah,
cool.
so-
Sorry to interrupt you.
No worries. So Jake and I come from an AI background, and then same goes for Isabella and Eugene and Taco. Myself, I'm
Yeah.
been doing AI for the last 10 years or so. Did grad school in that, graduated with a PhD in 2017. Jake comes from basically DARPA project background. He's more industrial end of things. He's been working also for Google for a while. And then Eugene and Isabella are, I guess I can leave it up to you guys to kind of describe it. But for Taco's end, he's not here. He's also been in AI for a long time. He's been also a PhD researcher out in IBM for about, I think about 10 years at that point. He's been there for a long time. So we all come from an AI background, but Jacob and myself kind of have a bit more of a blockchain experience background because we're the ones who are kind of working on the blockchain end of things, and we're kind of trying to expand that in hiring a bigger team. But pretty much everyone on the team is an AI expert.
That was mighty interesting. Thank you for that.
Yeah, no problem.
Yeah. I think you know what I found very interesting is that you guys chose the blockchain technology for decentralizing AI. It's absolutely beautiful. It's beautiful. It's Asimov. You know when I think about
Well
it.
said. Well said.
Yes.
Yeah.
Yes, it's beautiful. So I want to definitely thank you guys for it.
Well, thank you for being a part of it. It's gonna be great having you on board, and it's gonna be really great to kind of move forward from this.
Yeah.
No, I'm just saying the main reason we picked it is just because it made sense, right? So like a lot of these projects that I'm sure everyone's heard of, they kind of use these kinds of AI blockchain buzzwords just because they want to make a quick buck or it's some Ponzi scheme or whatever. We're kind of approaching it from the different end. We're saying this makes sense because it is a utility, it is a commodity, and we need to incentivize it that way.
Yeah. I mean, I was working on building brain chips at DARPA, and then I just decided I have to work on something just as cool. So, the only thing,
If not
the
cooler,
only thing
Jake.
is remote.
That's beautiful. That's really beautiful. It's like I have one of my best friends. He was working on military equipment. Like he's an electromechanic master, and he switched to building drones. And he said the same thing. Like it's absolutely beautiful to change, to do something crazy.
Yeah, it's very liberating for sure.
Yeah. So I really like the choice to have a decentralized AI on a blockchain. Absolutely beautiful. So, okay. Thank you, guys.
Yeah, and it's at first a lot of people are skeptical of the idea because there's been so many projects that have bastardized the idea by just claiming the buzzword. I mean, I hope there's nobody from SingularityNet here in this chat, but that project is a really good example of people scamming others that have no idea what AI is. So they were like, okay, let's just use blockchain AI, and then people will give us a bunch of money, and that actually did work. But me and Ala were around when that company was formed, working on Bittensor, right, and trying to solve the underlying issues that we knew needed to be solved to actually accomplish that. And we decided not to launch in 2017, even though that there was a lot of demand for a project at that intersection. And you could say we may have even missed the 2020 cryptocurrency boom. Maybe not, who knows? We're still kind of in it.
I think with general development in AI, this is the right moment. I think it will be the next 10 years, 5 to 10 years. It's the coming decade, the fourth technical revolution per se, something like that. It's the next decade. AI, new materials, space.
Well,
yeah. Interesting
and
times we live in.
and AI is actually, due for another inflection point. I think that we discovered deep nets in like 2010, and that was a huge inflection point for the field. Really kicked off another golden age, and we're now kind of reaching the limits of that system. The train a model that's really big with lots of parameters on a lot of data, and then release it into the wild, for a number of reasons. And I think that's what we're trying to fix. We're trying to fix the meta system that's actually creating AI, right? We want to work on the efficiency of the buildup of machine intelligence, right? We want to make sure that there's just a global buildup of intelligence that's accessible at all times. We want to combine the compute power of people across the globe in ways that is not possible with standard corporate structures, and we also want to combine the ingenuity of people from across the globe in ways that right now the academic competition is essentially limited. There's a lot of really, really, really smart people out there that work in AI. The field has bludgeoned. There's 14,000 engineers that are writing papers and research papers and to go to NIPS. We want to reach them and give them a completely new avenue to make money, and also to innovate and not have to worry about writing papers and getting a NIPS. They can just monetize their work directly. And so what we're doing, I think, is kind of at the intersection of things, right? There's a technical reason for what we're doing. There's also an ethical and humanistic reason for what we're doing. Yeah, but it's also a good question, who the fuck are we, right? Why? I mean, I think we're kind of the two first team members of Bittensor after Yuma, and we're a great team because Ala actually has a lot of academic experience, whereas I'm more of an engineer, work from industry, know how to build systems and not write them down in papers.
Ouch.
Well, how old is the AI field? The field of programming, quite decent AI. How old is it?
I think at this point.
The field of AI goes back.
Yeah, the programming of the development of the first NLP data sets that were developed and such. What time was that?
Long time ago.
Long time, yeah.
Long time.
But AI as it exists today, from a framework perspective and how it is to create a neural network and stuff, is, I would say, fairly recent. Maybe, I don't know, within the last 8 to 10 years.
Yeah, but you guys say, very old. But when was it? I actually really don't know.
So I actually have a fun fact, and it's time for me to put on my professor hat for a moment.
Yeah.
The really cool part is all of these neural nets and all of this AI stuff has actually been around since the 60s, but they never had the tech to actually develop it into something. It was just theories and statistics. It was more until recently in the 90s and 2000s where people were like, holy cow, we can actually apply this and it actually works. So my next question is, how high were the people who created this in the 60s that they came up with these ideas and they still work mathematically?
Rosenwald. He was a genius.
Yeah.
And even Turing, right? So like Turing wrote about AI in the 1950s. You could say maybe he was the fathers of modern AI, if you call 1950s modern. And he envisioned adaptable systems built of components, something like neurons. And there's sort of two fights in AI that are ongoing at all times. There's the ontologists, and then there's the compute people. There's the people that go, hey, let's actually try to encode mathematically the smart answer to a problem. And then there's the people that are just like, well, let's just throw more adaptive structure under compute at the problem. And Turing had that idea back in the 1950s, but they just didn't have enough compute to create the neural networks and the statistical models. That they didn't have enough compute to run the statistical models that could find the solutions in a machine learning sense. And so
I think that's also that's why I also like the names you chose, so the axons and the dendrites. It's like the metaphysical brain of AI. You've given we say in Flemish, we say you've given the child a name.
Yeah. And some people think that decentralized AI is a stupid idea, but if you look at the way that intelligence grew in nature, it's absolutely decentralized. It always is. It's adaptive components.
Absolutely.
That work together, like a neuron. But then the thing that they're adapting to something, right? And we're the first project to go, that thing that they can adapt to is currency directly, right? Instead of they're adapting to a loss gradient, which would be the standard model of the last 10 years, we're going, we can adapt this system directly to the flow of currency. And then nest the pursuit of artificial intelligence, you could say maybe even like at a higher level, right? We can build the incentive mechanism under which the adaptive components adapt to a gradient in the standard model. So we're doing meta machine learning, and so that's really where a lot of inspiration comes from. This is really taking that secondary thread of, okay, well, let's build more adaptive components and put them underneath a trading signal of some sort, in this case currency, and then throwing the swarm at it. That's been the solution to most problems in AI for the last 10, 15 years. In fact, over the last 50 years. And so we're kind of extending that. Ship, maybe you can adapt what I said in layman's terms.
No, I think you kind of nailed it on the head. There's no better way to say it, really. We're kind of just building, we're standing on the shoulders of giants in a lot of ways. That's the best way to put it down.
Yeah, it's kind of a shock that it hadn't been done before.
To be fair, it has, but within internal corporations, within their massive compute, and even that is obviously limited by how much compute they have, and we never get access, we never get to see what that is. We just see the end product, which is, living inside your Google Homes and your Siris and stuff like that.
Right. But also like the technology we're building on top of right now is Substrate, allowing us our own chain, our own data, to integrate with other chains. None of that was really possible until, 2 years ago.
Actually, that's a good point. Yeah.
Not even 2 years ago, and so we're lucky to kind of be at the intersection of a bunch of different technologies together.
I think it's, I never say this, but I think it's kind of a right time, right place kind of situation. Right place, right time. Because, yeah,
Could you guys maybe answer something for me? So why is the financial world so interested in the NLP data sets and technology?
Well, when I worked at Google, to give you an example of how valuable machine knowledge is, if we were able to improve the performance of one of their machine learning problems, let's say like predicting advertisements for a user based on the text in an ad, you'd actually have a model that learns from the text and then predicts whether or not this particular person, given everything that they've written, will click on the ad. If you can improve that by 1%, it's something like $1 billion extra per year for that company. Google obviously being a pretty big company, right? 100 and something 25 at the time. I think it was $125 billion per revenue per year. So they make a lot of money, and the margins of improvement are slim, but when they do make improvements, they're substantial. And I think there's a lot of companies like that where 1 or 2% improvements in the accuracy of something that's text-based can mean billions or millions of dollars worth of value to them. And so that's the market that we want to touch into. We want to go, hey, look, you can do 1% better, so buy $1 billion worth of tech, right? Maybe Al, you have a better answer to that?
No, you kind of nailed it. The other bit here is I want to add possibly also due to all the data scraping that needs to be done off the internet, right? Everything from early news to like even stock sources can affect the price of certain financials, right? So scraping that and finding the right keywords at any given point is.
But is the data, is all the data that is available digitally interesting? That's always something that.
That's the problem, right?
My mind, like.
Is it interesting?
Like.
Yeah, that's the problem. Is it interesting? And that's why they have a lot of models to actually verify this.
Yeah, because yeah. Well, okay.
It's not. I think that we've moved in the world of. So 5 years ago, everyone was talking about big data, right? Big data. I got lots of data. It's
big data. It also showed that it didn't work during Corona, actually, with all the predictions and all the. It's big data. Yeah.
It's not big data. It's not about data anymore. It's about understood data. There's so much information being produced by humanity every day that what really matters is can we even understand that information? So that's where intelligence comes in, right? Is the understanding of the data that we're producing.
Yeah, but what I wonder about is if all the core data is digitalized yet, because you have a tremendous amount of scientific writing on the internet, but it doesn't necessarily mean that the core data of our cultures are all perfectly digitalized and set into digital data, I don't know if the complete book of Archimedes is 100% set in digital data, and it's one of the basic works in understanding of mathematics historically then, so it's like the colleague I have at work that says, Dimitri, I never read books, because everything is on the internet anyway. Mm-hmm. And I always say, Jorn, it's not true. You have to read a book once in a while. But I also say to my colleague, I say, you're also right,
Yeah, that's a really good point. The models that we train can't learn everything because they just don't have access to everything that exists in the world. Like they don't have the physical embodied human experience, for one. They're not out there walking through the green fields or whatever. I mean, they can watch a video, but they're just not actually there. So perhaps there's just things that we'll never learn. But that being said, there's so much on the internet right now that just trying to understand that would be a it truly is a tremendous task. The holy grail, in my opinion, of what AI will achieve is a representational model, like what we're training right now, something that can build a representation, like a map of the entirety of the internet. And it does a good job of understanding everything. It can predict every tweet. It can predict every image. It can understand every image. Sort of the ultimate the ultimate AI brain of the internet, be able to understand everything that's going on, all the books, all of the tweets, all of the Reddit posts.
Processes everything all the time.
Could we have Samantha? Like, have you seen the movie Her with Joaquin Phoenix?
Yep.
Can I have Samantha?
Probably something
I want
close.
Samantha.
Probably
we have
something
Yuma
close.
Rao here.
Say again.
I'm saying, like, instead of Samantha, you can have Yuma Rao.
Exactly. We'll have Yuma, but Yuma is his own person. We don't even
I'll
know
have
who
a
he is.
Yuma. I'll have a Yuma. Yeah, that's cool.
Suave voice of Yuma, always whispering into your ear. I'd take that.
It kind of sounded like I was reading a paper written by a ninja, to be honest. Yuma Rao. It was like, fuck yeah, I want to read this stuff.
You're not wrong.
Hey, Gimmick, are you still on this call? Is Gimmick here? I think I see him here.
I see him, but I'm not sure if he's speaking. Probably not.
Yeah, you had some questions about the data set. Can you maybe be more specific so we can talk to that? You can also unmute yourself if you wanted to speak directly to how can one use it? Okay, so it's more of a technical question. Well, you can use the Bittensor API. You just import Bittensor. You create a data set connection.
We can't really see your screen, by the way, Jake. If you're trying to show something.
No, I'm actually just typing this in.
Oh, I see.
And then you call next on that data set. It's an iterator, so that will give you access of tokenized text. You can change the data set up. It's basically just like a data loader. If you ever interacted with those before, I believe this works. So that would.
Do you want to describe a little bit for people about what is behind the data set?
Yeah, that's a good question. So behind the data set, so we've been working on this. Actually, there's something I didn't even mention in our slides, but it's been a big push for us over the last couple of weeks. Is taking the data we have. So it's all unlabeled text, various sources, for instance, just like Reddit posts or archive papers and Wikipedia. All of that text is loaded into text files, which we host on IPFS. So IPFS is like the back end. And so these text files become two things. They become the source of information for training your models. It's the same data set that was trained, roughly the same data set that trained GPT-J. So it's a real data set. It's a very useful one. It becomes the data set against which people can train their models, but it's also the data set against which people are evaluated. It's important to keep that up. Validators are evaluating the models in the system against that data set. So it's important that you're training from that data set when you host models. Okay, so that makes sense. I'm glad that makes sense. Cool. Did it answer that question well enough, Eugene?
Yeah. So I think right now we have approximately, to give people an idea of how much data we currently are hosting. I believe we have, Alec, correct me if I'm wrong, there's about 800 gigabytes of data we're storing on cloud right now. And anytime you're polling...
Should be double that.
Okay, is it double that?
It's about 1.6 terabytes. Yeah.
Okay, yeah, so 1.6 terabytes of data that's currently various books, text files, emails, Maybe you can think of it. It's probably if you can think of a book, it's probably on there. And we have had that hosted on the IPFS, which is the Interplanetary File System, for people who are familiar with sort of more of the decentralized protocols. The IPFS was created by the people who made Filecoin, I believe. Yeah, Filecoin, and and that's the backend to our data set.
It's okay. So that's a great question, by the way, from Barbara Seville. So in classic, the question is, how do you stop bad actors from just overfitting on the data set to maximize their since validators value? So this is a really good question. And it comes down to the difference between supervised and supervised learning. So in a supervised learning setting, you can just memorize the data set. So you can build, let's say you're classifying images. You can just encode every image with a unique tensor into your embeddings, and the model will just learn to project from that unique encoding. So it doesn't actually learn to generalize, because the model has just learned how to directly to memorize each of the inputs in the data. So that's a big problem when you have a data that's quite small. So, or 60,000 images in MNIST, for instance, where you just memorize the data set and you actually fail to generalize outside that data set. So you don't even do a good job of recognizing written text images. Now, in unsupervised learning, however, the data sets are really, really large. So 1.5 terabytes of text. The ability to memorize and encode every sentence in a way that would allow you to predict the future sentences. Let's say you're trying to encode 1.5 terabytes of text into an embedding size of 1024 in such a way that it's just a memory lookup, would actually be solving the problem that we're wanting to do, because the data set is so large. Memorizing it inside of an embedding space that's small actually just would require you to extract the semantics from the sentence, because that would be the best way of encoding it. So the overfitting is no longer really an issue for training these unsupervised language models across large data sets. And in fact, if you train GPT-3, when they train GPT-3, the model never converges, right? So there's never a point where it actually overfits. You can put as many parameters as you want, and it just doesn't overfit. That's a really good question. I think the follow-up question is it's more of adversarial resistance if they try to cheat on building the embeddings. But this is something we were talking about before in the keynote, and I won't deep dive into that because we haven't actually pushed that update yet. So we won't talk about the actual adversarial attack that can be done, but the one we just saw. Hopefully that answers your question, Barbara.
Cool.
Okay, awesome. Sweet.
Awesome. We have a few minutes for a few more questions, if anybody has anything.
Shreyash, give me a really hard one. Shreyash is a Mila machine learning engineer, so he's probably got a really good question for us.
I don't think so. I've been trying to scale my operations, and I do think there's a bunch of like adversarial things you could do for the network that would basically like mean that we would break the network to some extent. Like you could do the thing where you only assign weights to the, like if you have validators, you only assign weights to the ones that you have that correspond to your servers, right? And sort of overweight those servers, especially if you have a bunch of tau. And those things would have to be dealt with at some point in the future, right? Like, do you guys have ideas and plans on how to deal with them, or like just like the network becoming so large would mean that that isn't a profitable strategy for most people at some point?
Well, we think it's so right now, right? the the attack that you're talking about, the cabal creation, the measure that we want to calculate is how much better would you do as a bad validator over a good validator, right? Because if you could just validate properly, do better, then that's what you want to do, right? So that difference is our adversarial resistance. So right now, the defense is simply that the system is actually backed on the Open Tensor Foundation validators, that doing that would you don't have enough tau to do it to really overcome the consensus. As you build up more and more tau, so we have a couple things in mind that I maybe talk to you offline about that will make that really difficult. I think one of the major ones is actually forcing peers to set weights to more than a small cabal, so you can't create a small network. Right now, we've been investigating to see if that's possible, and no one's doing it. It's great, it wouldn't make sense to do it anyway. But I think one of the defenses right now would be to force people to have a certain number of weight outward bandwidth, so fan out on their peers, and also we want to potentially update the bonding mechanism to make it even less profitable, or less profitable for people to do it. I think it comes down to really that.
Yeah, I think as long as you have a system with enough validators such that, like you said, being a bad validator is bad enough that people won't do it, and the servers that they're sort of prioritizing aren't actually good. Like if they're actually good and I'm sort of prioritizing my own cabal, maybe that's not a bad thing, because I think of Bittensor as somewhat like proof of productive work, because I think ML is sort of productive compared to doing math problems for Bitcoin. So if the models that I am prioritizing are actually better, then maybe you're not doing a bad thing, right? Like you're still like not playing the fairest game, but you are still positive sum for the network. Whereas if your models are bad, then nobody else should think they're good, and that will mean you're a bad validator and you make less money, and you're sort of like sum of all the tau you can make across all your means, it should be lower than what you would just make through the validator. I don't know how to mathematically frame that, but yeah, that seems like it should be something that should be possible.
I can show you some of the calculations we've been doing. Yeah, I think you'll be quite interested in that. But moving on, Yosh is in the room. If you guys can see, he's at the bottom of this channel. Yosh is one of the HiveMind guys. He basically designed the RPC system that is core to what Bittensor is with the rest of his team. Yosh is an absolute genius, and stoked to have you here.
While it is very good to see you again, it wasn't me. That particular part was designed by Maxim Rябinin. I was just answering your question when you asked. Second, please don't attract too much attention to me. I'm just lurking. And third, great work you've done on the dataset and data loading from IPFS. It's really cool. We're studying the code now. It's just, again, super cool way for general decentralized training. Thanks.
Don't study too deeply. We're still,
It's still barely working.
We'd be happy to tell you everything that we've learned about IPFS. We
have very strong opinions about IPFS at this point.
That would actually be great. Do we have time for a couple of quick inquiries?
Yeah, of course.
Go for it.
So full disclosure, on HiveMind side, we were investigating, the previous technology, the torrents, they still didn't have, the BitTorrent, the regular one, they still didn't have concentration, yet we tried to kind of somehow screen loading huge data set of images. So first, that didn't work. Second, we're now looking at IPFS kind of conceptually, and again, learning from the great work you've done. One kind of weird thing is, the dataset is huge. How do you partition it? How do you kind of actually assign like atomic objects out of this huge dataset?
You had to be do that, Eugene? Is it just 1 megabyte files?
I was just going to answer that one. Eugene, do you want to take it, or do you want to jump on?
No, Ella, you did this part, so.
Okay, yeah, so effectively the dataset that we're using was actually initially compiled as a bunch of JSON-L files. Each file was pretty massive. It was 30 files to about 1.6 terabytes, a couple of hundred gigabytes basically per each file. And what we did was we literally just extracted each file basically described a bunch of different, so for example, you can have one file that has a bunch of books in it. We extracted each book out of each file. So on average, each individual file downloaded from IPFS is a couple of megabytes in size. And so the way that, part of the reason we did it this way is to also preserve some of the integrity of the file. So for example, if we just chunked it out to, let's say if you have like 2 or 3 books and they get divided into 6,000 files or something, you might end up with weird discontinuities. So what we ended up doing is kind of preserve the actual content, but at the same time, when you download a specific file using the IPFS dataset, you're downloading the whole file at the same time. So you end up with a bit of a SIP essentially. And then the Bittensor API, the way it's designed is that you can actually specify how much you want to download. So let's say you want to download 50 megs, you want to download 100 megs, you want to download 100,000, whatever, and you go from there essentially. The initial data set itself is actually the pile from ELUther. So that's why we kind of got a really neat start, because they had compiled it pretty nicely and we went from there. But moving forward, we're also looking to pull things like column crawl and stuff like that, which are pretty massive, probably even bigger than like 5 terabytes.
I see. And if there is enough time, so again, thanks. First, thanks for explaining. It's great to know how it relates to file. I didn't know that. Second, in general, like assuming you want to do something like this for images. So just again, as a context, there's recently been like bird-like and like transformer-based, very similar general pre-training for images. And so the only problem with the images is that they are like an order of magnitude bigger. So would IPFS in its current state tolerate loading like a 50 megabit per second stream of images, or what's the expectation?
It should be able to do that as long as you properly distribute it. So the tricky part about IPFS is that it caches your images out. So it doesn't work like you expect it to work. Let's say you have, 10 computers and each have IPFS on them, and then you have one of them that's hosting everything. Basically, each computer that gets a hop from IPFS caches that image that you're pulling in. So you'll have to be careful in how you host those images, because if you end up with, for example, 10 computers with each of them hosting a portion of this image dataset, you might get duplicates because of the way that IPFS works. It tries to cache it even though there's a duplicate. That's one thing we're actually trying to investigate right now, if it's a quirk in IPFS or if it's a quirk in the file system that we're using. Because ideally, it shouldn't be creating duplicates. It should be just creating pointers, right? So, yeah, I was going to say, it exacerbates the problem. Go for it.
Yeah, please go ahead, sorry.
I can add one more thing to the actual size. So the actual size of in IPFS, the actual size of the files that you're trying to add to the system doesn't really matter. IPFS by how it's designed, we will start sharding smaller and smaller leaves, which when you call for the upper node in the tree, will collect all of its sharded files and recreate the same image or whatever that you're trying to create. So the actual file is not too big of a problem, but if you're trying to load in like a file stream of a couple of megabytes per second consistently, and that can sometimes be an issue depending on how you're hosting the images.
I see. So again, I'm both like it definitely depends on like who exactly is sharing it, like where do you actually stream from. I definitely understand this argument. I was only a bit concerned about, so for instance with torrents, there is a huge just kind of technical overhead for merely beginning to download stuff, and with torrents we ended up having to like have a buffer of like 10,000 images and downloading that in advance. So when somebody just joins the ban torrent now nothing network, they would have to like wait for 5 minutes, 10 minutes before they could stream. does IPFS work any better in that regard? So like, is it possible to quickly download the content that you want, or is it the same?
Do you have a number on that?
So I don't know exactly the overhang that we requires download, but we can actually make it so that it's hosted on a server, and then you can just make individual API calls or whichever images that you need, or whichever files that you need. That's at least the way we do it, and then you can continuously stream that. It's like just like any HTTP call, so it's not. I don't believe there's too much of an overhang, but correct me if I'm wrong, Ella.
Nope, you kind of nailed it on the head there.
If you wanted to test out how fast our method is, I posted in the general channel. You could just measure that. I think would tell you how quickly we produce tokenized sentences, batch size 10, block size 10. That would be like a proxy for how fast, because the way it works right in the background, you have thread or a process that's just filling a queue, and then we just pull from that queue. So that would at least tell you how fast our implementation is, but that's not as fast as it could get, because I think that's just a few of our servers. But in the future, we think that we could probably speed things up by having more people running IPFS nodes, right, Eugene? That would speed things up because the caching would be much better, right? Across the line.
It would be a similar effect. It would be a similar effect to having people run their own subtensors, right? Everyone would start basically speaking to each other, and they'd be a little bit more decentralized too, at the same time.
Yeah. So, but anyways, that minimal example, Yash, would tell you how fast we can pull out data and tokenize it. Given, I think, how many endpoints we have, Eugene, on DigitalOcean? 10.
So we currently have right now, if you call it just by itself, we're only using 5 service nodes. In the coming update, we are going to be introducing more support for people in Europe, introducing additional load balancers there. Then we plan to basically, as we continue to globalize, introduce support across the globe.
Yeah.
Sorry, if I may. So then, understood correctly that the setup is that the basically the data itself physically is sharded, but like I mean, the IPFS is used to kind of maintain the data and get the data on those servers. And when like I launch a new kind of miner, it would just download. It would just stream data over HTTP, not using IPFS as a protocol, right? Is this the case, or did I miss?
No, you're effectively right. IPFS, actually, the API itself is HTTP based. There is no like WebSockets or anything going on.
Yeah, that makes sense. Totally. I was just wondering. And kind of another minor comment is like, it's actually a really weird, not just with the image, but in like the rate at which you need to stream the data, because like the bigger model you train, the less data per second you need for obvious reasons, because your GPU can only do so many samples per second if it's like a transformer, gigantic, whatever.
Mm-hmm.
So again, like it's probably gonna, like, it's not the question of how fast can we make it theoretically, it's the question of how big a model should we train to make the current data loader feasible.
That's a very good point, actually. We haven't reached that point yet to actually start balancing between the data loader and the model. Right now, they're kind of just two modular entities, but the future, like for the future, we're looking to actually create custom data loaders and, as you said, model-aware data loaders as well.
Yeah, thank you guys a lot for explaining. I guess I'll stop bothering everyone and just shut up for a while. Thanks again. Cheers.
No, good questions. Ping us anytime.
We hope you come back and bother us, Josh. I think one of the takeaways maybe about IPFS was that this morning I think we were seeing IPFS for various reasons. You may even, and I know that you built nearly as from the scratch, so maybe you'd actually do a better job of writing it yourself. Yeah, maybe. So.
Well, theoretically, given infinite time, somebody could, but like we're living in this weird universe where working is better than perfect.
Right. Time is of the essence. I understand. Okay, cool. Well, yeah, thank you so much, Joshua.
You guys, I was asking for help. You provided help. Why are you thanking me?
Cool.
Should we? Any more questions?
I see one question coming in from Barber. I'll write it. I'll answer it. He said, "What about image subnetwork? How do you imagine those validators would work since it's possible to fit on image data?" And so this is actually really cool. And Josh pointed it out when he came in that modern is it Josh? Correct me if I'm wrong, but state of the art on image now is unsupervised.
That very recently changed. So actually, there's a paper called "Masked Autoencoders as Scalable Image Learners," and that was basically the last straw that kind of crashed the camel's back. By that I mean basically they are now significantly better at a decent scale for many production use cases. So like I'm a corpo sellout and I do corporate machine learning as well, and in our domain basically it is now the point where pre-training as a masked autoencoder, basically BERT, can give a better quality than like going to great pains to actually kind of label a reasonably good labeled data set. So it's not kind of absolute ubiquitous victory of pre-training unsupervisedly, but it is very close, and in many cases it's already kind of just got past the barrier. And by just I mean like not that far.
Yeah. And
so this one.
Okay, cool. Are we watching your stream on purpose, Josh?
I was just showing the paper specifically just to
We
state that.
did see it.
I think you were just showing your Discord screen, unfortunately.
Oh, I'm sorry then.
Did you just post the link in the channel? I think that's probably.
Yeah.
Which channel? Sorry, is general fine?
General's good.
Yeah, general's perfect. But yeah, to answer your question, Barbara, Josh is pointing to supervised representation learning in image, which is showing that the field is actually moving to unsupervised learning. That's where we were going, and then the field has sort of also concurred with that. Everything is going to be unsupervised, we predict. All the things. There'll be no supervision. No one, will say yes or no to anyone else ever.
It's like Jake's stream.
Right? You'll go to school, you'll be a university, and you'll just write whatever you want on the test, and the teacher will just go, unsupervised learning is better than supervised learning, and way to go. Here's a star, and yeah. Anyways,
I miss getting stars.
Judging by the way we're currently moving, at least on the test, you will be very good at filling in the blanks in text, filling in the blanks in images, filling in the blanks in sound, filling in the blanks in whatever. Yeah, it just somehow seems the way we're going. Actually, also the same thing in sound. There was like Data to Vec, I believe, which is an extension of BERT and this idea, which is basically the same to sound, where they also produced very, very compelling results. Well, I'll just be adding a few links to that post. Again, sorry for intrusion.
No, not at all. There was also the you of course saw the unsupervised learning paper from Meta AI or Facebook or whatever, that recent one. Was that what you were talking about with regard to doing multimodal? Yeah, that one. Yeah, Data 2Vec, exactly. There's the everything encoder. That's the dream, right? The embedding for all things.
And actually, they, to the best of my knowledge, mostly focus on one machine learning algorithm to rule them all. They don't really do massive cross. They don't try to combine image and text in the same representation. But I guess your friends over at Leon may have something to do with actually building a unified representation for image and text.
That is actually probably what they're working on, yeah.
I thought it was a unified representation. It's not? It's not a unified representation? I thought it was.
Their main area is like they have a unified mathematical kind of loss function and optimization algorithm.
I see. The unified training
And-
Yeah.
Yeah. So like what they do is basically they do masked autoencoders, but like in this weird intermediate model space. They mention many times the results about mixed representation, but basically if you look, for instance, at what they publish, like they have a code in FairSec, which is Facebook's standard. Like basically it should be metasec, but that doesn't rhyme as much. So basically they have like a separate model for sound, and it's published, and they have a separate model for vision, and it's not published because for some reason they didn't yet, and like they're separate, unfortunately.
Right. But it's still an incredible result that they're going that direction. They probably will go multimodal in their next paper. And then did you also notice that they use as the main approach for actually training the system in the it's like what is it, self distillation or that they're doing. But we can adapt that same method, Yosh, to Bittensor, and there's actually a couple really cool things, right? So they mask the local model, and they don't mask the remote, and you only need the embeddings from the remote that are for the mask during the training step. So if you're, say, a client to Bittensor and you're training your distillation model, which is the end goal, you just send your inputs over the wire, and then you also send the mask. So you send, hey, like I only want embeddings 10 and 50 and 100 as my targets to train my distillation model, and that's what you return back to the client. So we think it's actually in their method, they actually figured out a way of also reducing the training, the bandwidth considerations for decentralized learning as well. It's pretty cool.
Yeah, again, you know way more about Mean Teacher than I do, but it does indeed sound very intriguing, and kind of it's as though folks at Bittensor started thinking about Mean Teacher before it went cool. Because like you talked about distillation of like the collective kind of model, I remember back in 2020.
Yeah, but I mean, Hinton takes the cake for that, I think.
Well, yeah, but like the big part is about like the way that it kind of naturally fits with the idea that you kind of distribute this, that you distillate this collective model that you couldn't possibly fit on a single device. This one, like, it's not specific to what's happening now, it just kind of naturally fits with Bittensor.
Yeah, it at its core, that's really the method of information transfer. It is distillation through which the transfer is occurring.
Yep.
Your gift. Yeah. And that's quite a moonshot for us, right? Like we're tying our boat to that dock, right, with distillation. And I think that's probably, sometimes people ask us like, what's the technique, the machine learning technique that we're least confident about, like the one that there's the most uncertainty. And I think distillation is still it, because we're still just beginning to really understand how distillation works, and everything else, like mixtures of experts, it's understood, right? Language modeling through representational learning is understood. Everyone knows that it worked, right? But distillation is still a big question, I think.
Well, there is indeed a reason why the original paper says distilling dark knowledge. Yes, I guess you're not alone in not understanding how distillation works.
Yeah, exactly. It's like, exactly. It's like dark matter, right? Like, where is it? Yeah, great to have you here.
And well, just kind of as a passing thought, actually, like, so, well, from what I believe, the original kind of commotion of what like you're doing in Bittensor and what we're doing in HiveMind and many other projects was like basically, okay, those guys have like 100+ billion models, but they are not sharing. Let's do something better together. And the weird thing about like distillation, well, let's just say all those foundation models, trademark, GLAM, GPT, let's just say even if they were to give them away, like even if like, I don't know, OpenAI accidentally pressed a button and now you have the parameters, you can't really inference it on like anything that you can like, that's not like HPC grade mini supercomputer. And in a way it would look like that might also be the only way for them, because like in order to just inference GLAM, the latest Google's take on large language models, they have an entire kind of small scale cluster there, and if you want it for anything more kind of flexible for edge inference, it just doesn't work. So maybe the distillation is the answer there.
Yeah,
so,
we're kind of pulling in two directions, right? It's like from one side we're like, let's make fucking massive networks, and then the other side is, well, hey, they actually be able to run. And we know, I'll be honest, before this I didn't even really realize how much compute you needed to run these large models. Like to inference in a reasonable amount of time GPT-J, you need 64 gigs of RAM, and that's only 6 billion parameters compared to GPT-3, which was 178. You know.
And I have specific numbers for this one, unfortunately, because in like there's this collaboration called Big Science about like just figuring out how to train exactly GPT-3 like models at like cheaper but still among supercomputers. And like if you have a single V100, then the full GPT-3 for a single forward and backward pass, even if you disregard memory, takes something like 4 minutes. So
oh my god.
Wow.
Oh my god. That's
so like it's just to run it one way and then the other way for a single sequence. So
oh it's so slow. It's incredible.
So folks, to translate, this is the current state of the art right now.
It's like a quarter of the current state of the art. Just to remind you, the 530 million model by NVIDIA and Microsoft pulled together is way worse in that regard.
Oof.
So, like, 1 terabyte of RAM is not enough to merely load the weights into the RAM, and then you need to somehow transition this to the GPUs.
Yeah. This was actually, when I first graduated from university, this problem that the company I was working at was they were trying to figure out a way of doing like legitimate, like huge scale machine learning, but way faster. Because the thing is that our compute infrastructure is actually just not designed to do AI. It's the CPU and memory are separated on computers. There's memory and then there's the CPU, and every time you want to do evaluation of something, you have to pull it from the CPU, from memory to the CPU, which is just super slow. And then, but if you compare that to say like, you know, my mind, something like what is it, 100 trillion, 11 trillion synapses, right? If you were to try to actually, like if a forward pass on GPT-3 is only 178 billion, and that's 4 minutes or something. Think about how slow 11 or 10 trillion synapses would be on a computer, and so the company that I was working for was trying to actually build synapses themselves. They were actually trying to build synapses.
So like and hardware that specifically does this neural network, or like
yes, but you could train it. You could, and so that you would actually fire every single parameter at the same time. Like there was no serialization of the network. It was just the whole thing, and then you fed it through it, and then that was one pass was one clock cycle. So you could actually, then that's how fast things need to get, really, for machine learning to compete with human. That was the point of the founder of that company way back when. Well, that's shocking, Josh. Thank you for giving us that number.
We're going to use that from now on.
Oh, and if I can borrow another 30 seconds of your time, is it okay?
Of course.
So, like, one thing is that actually, again, it's huge, and another thing, as you said, our hardware is, again, not purpose-built for that, at least until very recently, because like NVIDIA have been thinking about like this super crazy fast interconnect with their Grace CPUs, etc. But like maybe like there's not just that. To be completely frank, I'm not really sure, and again, it's just me hypothesizing, but I'm not sure that even the standard mechanism, the standard building blocks of like normal deep learning models are built for the scale, because like if you think about it, like aside from this number of parameters, a single layer in GPT-3, like a single MLP, there's a like transformer attention and MLP. I'm talking about MLP. The MLP part is 12,000 by 49,000 matrix, and like this matrix is entirely dense. So like all the numbers, all the 10 to the power of 8 to low 9 are there, and that's not how brains work. So I mean, you don't have fully connected tens of thousands of units in your brain. And actually, like, I'm not sure if it's been in the spotlight enough, but like there's a resurgence of this idea that you can make them sparse, but kind of structurally sparse. You read this kind of scatterbrain paper, maybe the one from Stanford, that kind of tried to make the same very large models, but out of kind of smaller blocks that are interconnected in like a clever pattern instead of like all to all.
Right. Would that be similar to mixtures of experts, or is it?
No. So like mixture of experts is you basically you let the model decide any 3 or like any 2 out of like all possible connections, condition on the input, and it's actually way smarter than what the than what those guys do. Those guys do just a very simple thing. They just say, let me just post an image. I think I have it somewhere around. So imagine like a 12,000 by 12,000 matrix divided into blocks. So each block is like around 500 units. And the yellow blocks are there, and the blue blocks are just kind of zeros. Or you can scale it up, or maybe consider smaller blocks, but more of those blocks, and you get something like so this pattern, but repeated over itself like 4 times. And the idea is that each block is large enough to be GPU optimizable, but they're a fixed pattern, so you don't choose. In Mixture of Experts, you choose which ones you have. In this idea, they just kind of hard-code it and hope that the model itself would learn how best to use the fixed pattern. So it's kind of way less flexible, but hopefully, like, this thing allows you to easily implement it like in one GPU and kind of go beyond. Like Mixture of Experts operates on the level of kind of large experts usually. Like an expert is a layer, and this thing is like just a bunch of numbers. Is like just a small square matrix is like in each block. So
That's
again,
right. So you can potentially divide the computational power or computational load by some, huge factor, but then you're limited to these building blocks in the representation itself. Right, so you have to use, the neural network has to learn how to use these building blocks, basically.
That's what, like, yeah. So again, it's a relatively new paper. I cannot confidently say this is exactly what they do, but that's the intention, and that's what seems to happen. So their original paper is for relatively small models, but it still works. And we're currently experimenting with GPT-3 scale models, but with like way less parameters due to this. If we come up with anything useful, we will share it as soon as we get the result.
Fantastic. Yeah, thanks, Josh.
Yeah. Also, please don't use their code. Their code sucks. You can do the same thing like 4 times faster if you just like spend 5 minutes thinking what this matrix multiplication is.
Right, we'll share some of our problems with you too. I'd be curious to know the little things that are coming up that we don't have bandwidth to talk about talks, but we'll send them over to you, Josh, if you want to take a look at them and tell us what you think. Definitely more involved for than what we have guy. I think I muted him for everyone. Great. Well, what do you think, Alice? Should we end at 6:30? It's been an hour and a half.
Yeah, I think this was a really great event this time. So let's keep it up, and we'll see y'all next Thursday.
Yeah, thanks to everyone that came. Really cool to see you guys all here. Yeah, happy money. Ciao, guys.
Thank you.
Yeah, thank you.